Welcome to Tech with Kaushik. This is set 21 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam-ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 21. Here comes question number 374. We're working with troubleshooting here. Here's the scenario. A DevOps engineer updates an AWS CloudFormation template that defines the company's core networking stack. The update includes a new nested stack responsible for provisioning several Amazon EC2 NAT instances. When the engineer executes the update, the deployment rolls back because the nested stack fails to create. The CloudFormation console shows dozens of events across both the root stack and the nested stack, making it difficult to isolate the exact error. What is the most direct way for the engineer to determine the exact cause of the failure? Choice A. Enable AWS CloudTrail data events for CloudFormation. Query Amazon Athena for CloudTrail logs matching the nested stack ID to find the failure reason. Choice B. Use the CloudFormation detect root cause capability on the failed root stack to automatically analyze the event stream and highlight the specific resource failure. Choice C. Execute the AWS Systems Manager Automation Runbook AWS Support Troubleshoot CFN Custom Resource against the root stack ID. Choice D. Update the CloudFormation template to stream its deployment logs to Amazon CloudWatch logs. Search the CloudWatch log group for the exact error message. In this case, choose option B. Use the CloudFormation detect root cause capability on the failed root stack to automatically analyze the event stream and highlight the specific resource failure. The main reason is AWS CloudFormation provides a native detect root cause capability built directly into the console. When a stack deployment fails, especially in complex setups involving nested stacks, this feature analyzes the CloudFormation events and immediately surfaces the specific underlying resource error that initiated the rollback, saving the engineer from manually filtering through dense event logs. The other choices do not work because A. CloudTrail logs management API calls, but CloudFormation resource creation errors, like a failed EC2 instance launch due to capacity or permissions, are logged in the CloudFormation stack events, not necessarily in CloudTrail in a highly readable format. C. The AWS Support Troubleshoot CFN Custom Resource Runbook is specifically for debugging AWS Lambda-backed custom resources that hang or fail, not for general nested stack failures. D. AWS CloudFormation does not natively stream internal deployment event logs to CloudWatch logs. Stack events are accessed directly via the CloudFormation API or console. Here's a useful exam tip. For quick troubleshooting of complex or nested CloudFormation failures, rely on the CloudFormation native event logs and the detect root cause feature rather than third-party logs or CloudTrail. Next, question number 375. Scenario. A DevOps engineer oversees a shared AWS account utilized by multiple development teams. Corporate governance requires that every newly provisioned Amazon EC2 instance must be tagged with the creator ID and cost center of the IAM user or role that launched it. This tagging must be applied within minutes of the resource being created. The engineer has already written an AWS Lambda function that queries a mapping database to retrieve the correct cost center based on the creator's identity and applies the appropriate tags to an EC2 instance. AWS CloudTrail is active in the account and logs all API events to an Amazon S3 bucket. Which solution triggers the Lambda function to meet the tagging requirements? Options. Option A. Enable Amazon S3 event notifications on the CloudTrail S3 bucket for S3 object-created * events. Configure the notification to invoke the Lambda function to parse the log file and tag the instances. Option B. Configure AWS config in the shared account. Activate the required tags AWS managed rule and set the Lambda function as the auto-remediation action for non-compliant resources. Option C. Create an Amazon Event Bridge rule that filters for run instances API calls emitted by AWS CloudTrail. Set the rule's target to the AWS Lambda function. Option D. Attach an IAM permissions boundary to all developers enforcing the AWS request tag condition key during the EC2 run instances action. The right response is option C. Create an Amazon Event Bridge rule that filters for run instances API calls emitted by AWS CloudTrail. Set the rule's target to the AWS Lambda function. AWS CloudTrail integrates natively with Amazon Event Bridge. When a user launches an EC2 instance, CloudTrail captures the run instance's API call and sends it to Event Bridge in near real time. By creating an Event Bridge rule matching this specific API call from the AWS EC2 source, the event payload, which contains the identity of the creator and the instance ID, can immediately trigger the Lambda function to apply the tags, satisfying the requirement for fast tagging. The remaining options can be eliminated because A. CloudTrail delivers log files to S3 typically every 5 minutes in bulk batches. Parsing compressed S3 log files via Lambda is highly complex, slow, and operationally inefficient compared to using Event Bridge's native real-time event streams. B. AWS config evaluates configuration state changes and is excellent for compliance, but it operates asynchronously. It can take several minutes to detect the resource creation, evaluate it, and trigger remediation, which is slower and more expensive than reacting directly to the API event. D. While enforcing tags via IAM, AWS request tag is a best practice for prevention, it forces the user to know and manually supply the cost center at launch time. The scenario explicitly requires the Lambda function to look up and automatically apply the tag based on the creator ID. Keep this point in mind for the exam. For near real-time, event-driven automation, like auto-tagging upon resource creation, use Amazon Event Bridge rules filtering for specific AWS API calls via CloudTrail. Next up is question number 376. Here's what is happening. A DevOps engineer is optimizing a container build pipeline that relies on base images from public upstream registries, such as Docker Hub. Rate limits and temporary upstream outages have caused builds to fail. The engineer must use Amazon Elastic Container Registry, Amazon ECR, to cache the public images in a private registry. Whenever a new image is cached, Amazon ECR must automatically initiate a CVE scan so that scan findings are available in the private registry. Which solution meets these requirements with the least operational overhead? The choices are: Option A. Provision an ECR public repository. Configure a pull-through cache rule for the upstream registry and invoke a Lambda function to scan cached images. Option B. Provision an ECR private registry. Configure an ECR replication rule that targets the external public registry and enable basic image scanning. Option C. Configure an ECR private registry with a pull-through cache rule for the upstream registry. Configure basic image scanning with scan on push for repositories in the pull-through cache namespace. Option D. Configure an Event Bridge scheduled rule to run a code build job daily that pulls public images, scans them with a third-party tool, and pushes them to a private ECR repository. The best choice is option C. Configure an ECR private registry with a pull-through cache rule for the upstream registry. Configure basic image scanning with scan on push for repositories in the pull-through cache namespace. This works because an ECR pull-through cache rule synchronizes requested images from a supported upstream registry into an ECR private registry. The first pull causes ECR to create the repository and cache the image. Subsequent pulls can use the cache copy. Configuring basic scanning with scan on push for the cache namespace automatically starts a vulnerability scan when an image is stored in the private registry, without custom compute or polling. A. Pull-through cache rules are used with an ECR private registry, not an ECR public repository, and a custom Lambda scanner is unnecessary. B. ECR replication copies images between ECR registries. It is not the mechanism for caching images from external upstream registries. D. A scheduled code build workflow adds custom code and delay and duplicates the native pull-through cache and scan-on-push capabilities. The main takeaway is pull-through cache fetches and stores the image when it is first requested. ECR scan-on-push can then scan the cached image. Do not assume that a pull-through cache rule by itself is a pre-pull vulnerability gate for the first request. Now for question number 377. Next, let's move into deployment strategies. An organization is migrating a monolithic application to a microservices architecture on AWS. The new architecture comprises AWS Lambda functions for event processing and Amazon Elastic Container Service, Amazon ECS, services for long-running APIs. Both components undergo frequent updates. A DevOps engineer must design a standardized deployment pipeline that minimizes downtime during updates. The pipeline must support canary deployments for Lambda and blue/green deployments for ECS. The application also requires secure storage of dynamic configuration variables without hard-coding them in the source code. Which approach requires the least custom development effort? Review the options. Option A. Manage deployments using AWS Systems Manager. Implement rolling updates for ECS services and an all-at-once deployment strategy for Lambda. Store configuration variables in AWS Secrets Manager. Option B. Orchestrate the deployments using AWS Step Functions State Machines. Implement custom logic for canary routing using Amazon Route 53. Store configuration variables in AWS Systems Manager Parameter Store. Option C. Define the resources using AWS CloudFormation. Apply stack updates utilizing the update policy attribute to force resource replacement for all components. Store configuration variables in AWS Secrets Manager. Option D. Manage deployments using AWS Code Deploy. Configure canary deployment settings for the Lambda functions and blue/green deployment settings for the ECS services. Store configuration variables in AWS Systems Manager Parameter Store. The answer here is option D. Manage deployments using AWS Code Deploy. Configure canary deployment settings for the Lambda functions and blue/green deployment settings for the ECS services. Store configuration variables in AWS Systems Manager Parameter Store. Let's look at the reasoning. AWS Code Deploy is a fully managed deployment service that natively supports both AWS Lambda and Amazon ECS compute platforms. It provides built-in deployment configurations, including canary and linear deployments for Lambda and blue/green deployments for ECS, satisfying the minimal downtime requirement with zero custom scripting. AWS Systems Manager Parameter Store is the native service for managing plaintext and encrypted configuration data for applications. Let's quickly check the incorrect choices. A. AWS Systems Manager is primarily for EC2 fleet operations, not for natively orchestrating Lambda Canary or ECS blue/green code deployments. All-at-once deployments for Lambda do not meet the requirement for canary routing. B. While step functions can orchestrate deployments, doing so requires writing extensive custom automation and routing scripts, which violates the requirement for the least development effort. C. CloudFormation stack updates with resource replacement result in downtime and do not natively manage the traffic shifting mechanisms required for Lambda Canary or ECS blue/green deployments without hooking into Code Deploy. Exam tip. AWS Code Deploy is the native AWS service for traffic shifting deployments. It supports in-place/blue-green for EC2, blue-green for ECS, and canary/linear/all-at-once for Lambda. Question number 378. Consider this situation. A security team requires a standardized set of IAM roles and security policies to be deployed across every AWS account within their AWS organization structure. The enterprise frequently creates new AWS accounts for newly acquired subsidiaries. A DevOps engineer is tasked with ensuring these IAM roles and policies are automatically deployed to all existing accounts, as well as being immediately applied to any future accounts added to the organization. Which solution provides this capability with the most operational efficiency? Here are the options. Choice A. Utilize AWS Systems Manager State Manager to define an association that runs a script creating the IAM roles. Apply the association to all accounts via AWS organizations. Choice B. Activate trusted access for AWS CloudFormation stack sets within AWS organizations. In the management account, create a service-managed stack set containing the IAM definitions and enable automatic deployment. Choice C. Create an AWS code pipeline in the management account. Trigger the pipeline via an Amazon EventBridge rule watching for create account events, and use AWS CloudFormation to assume cross-account roles to deploy the IAM resources. Choice D. In the management account, create an AWS CloudFormation stack set with self-managed permissions. Supply a list of all current member account IDs. Manually update the list when a new account is created. Go with option B. Activate trusted access for AWS CloudFormation stack sets within AWS organizations. In the management account, create a service managed stack set containing the IAM definitions and enable automatic deployment. This is the best choice because AWS CloudFormation stack sets with service managed permissions integrates directly with AWS organizations. By enabling automatic deployment, CloudFormation automatically detects when a new account joins the organization or a specific organizational unit and seamlessly deploys the defined stack set, the IAM roles and policies, into the new account without any manual intervention, custom event routing, or pipeline scripts. Now let's rule out the other options. A. Systems Manager State Manager is designed to maintain the configuration of Amazon EC2 instances or managed nodes, not for provisioning cross-account IAM infrastructure. C. Building a custom code pipeline to respond to create account events and assume roles requires writing and maintaining complex automation scripts, significantly increasing operational overhead. D. Self-managed stack sets require the administrator to manually create IAM execution roles in every target account beforehand and manually provide the target account IDs, failing the requirement for automatic deployment to future accounts. When you need to deploy identical baseline infrastructure like IAM roles, config rules, or guard duty settings across all accounts in AWS organizations and have it automatically apply to future accounts, always use CloudFormation stack sets with service-managed permissions. Now for question number 379. Here's the scenario. A backend team deploys an Amazon API Gateway and AWS Lambda application with AWS code pipeline. The pipeline contains source, build, staging, and production stages. A previous release returned HTTP 500 errors immediately after production deployment. A later security review found critical vulnerabilities in third-party open-source dependencies. The team must add automated gates that stop a bad release before the production stage. Which two actions should the DevOps team implement? Select two answers that satisfy the requirement. Here are the options. Choice A. Deploy the candidate release to a staging environment. Run a smoke test against the staging API, and fail the pipeline if the smoke test returns a non-zero exit code. Choice B. Add a manual approval before the build stage, and require a security engineer to inspect every dependency before the pipeline can continue. Choice C. Run a smoke test against staging, but only publish a warning when the test fails, allowing the production action to continue. Choice D. Add the Amazon Inspector scan managed action before production deployment. Use source code scan and configure critical and high-severity thresholds that fail the action when the configured threshold is exceeded. Choice E. Deploy the release to production first, then rely only on continuous Amazon Inspector scanning of the deployed Lambda function to detect vulnerabilities. The answers that work here are option A. Deploy the candidate release to a staging environment, run a smoke test against the staging API, and fail the pipeline if the smoke test returns a non-zero exit code, and option D. Add the Amazon Inspector scan managed action before production deployment. Use source code scan and configure critical and high-severity thresholds that fail the action when the configured threshold is exceeded. Here's why. Option A validates basic application behavior in a deployed staging environment and stops promotion when the smoke test fails. Option D uses the current Amazon Inspector scan managed action and code pipeline to scan source dependencies and fail the action when configured vulnerability thresholds are exceeded. Together, these checks address both functional regressions and dependency vulnerabilities before production. Here's why the alternatives are not suitable. B. A mandatory manual review is slower and less repeatable than the requested automated pipeline gate. C. A warning does not prevent a known bad release from reaching production. E. Scanning only after the release is already in production is detection, not a pre-production gate, and therefore does not satisfy the requirement to stop the release beforehand. A helpful shortcut is this. Place functional smoke tests in a pre-production environment and fail the pipeline on non-zero results. For current managed dependency scanning and code pipeline, use Amazon Inspector scan. Amazon Code Guru Security was discontinued on November 20th, 2025. Here comes question number 380. This question takes us into high availability. Consider this situation. A startup recently migrated its legacy e-commerce application to AWS using a lift and shift approach. Currently, the entire application stack, consisting of a web server application and a MySQL database, runs on a single Amazon EC2 instance located in one availability zone. As customer traffic grows, The company requires a highly available architecture that eliminates single points of failure. The development team has limited capacity, so the DevOps engineer must achieve this with the least amount of application code and configuration changes. Which architecture redesign meets these requirements? Review the options. Option A. Refactor the application to run as AWS Lambda functions. Host the static web assets on Amazon S3. Migrate the MySQL database to Amazon DocumentDB. Option B. Migrate the web server application to AWS Elastic Beanstalk and deploy it across multiple AWS regions. Migrate the database to Amazon Redshift for improved analytical performance. Option C. Containerize the application and deploy it using AWS Fargate. Migrate the MySQL database to Amazon DynamoDB. Route incoming traffic using Amazon API Gateway. Option D. Separate the web server and database. Deploy the web server on EC2 instances across multiple availability zones in an auto-scaling group behind an application load balancer. Migrate the MySQL database to Amazon Aurora MySQL multi-availability zone. Go with option D. Separate the web server and database. Deploy the web server on EC2 instances across multiple availability zones in an auto-scaling group behind an application load balancer. Migrate the MySQL database to Amazon Aurora MySQL multi-availability zone. The main reason is the core requirement is to achieve high availability with the least amount of application changes. By moving the web application to an auto-scaling group behind an application load balancer, ALB, the compute tier becomes distributed across multiple availability zones without changing how the application executes. Migrating from a local MySQL database to Amazon Aurora MySQL multi-availability zone requires changing only the database connection string, providing immediate data redundancy and automated failover without refactoring SQL schemas. The other choices do not work because A. Moving from EC2 to Lambda and migrating from a relational MySQL database to a NoSQL document database, DocumentDB, requires a complete rewrite of the application logic and data access layer, violating the least configuration changes requirement. B. Amazon Redshift is a data warehousing service for OLAP workloads, not a transactional OLTP database for an e-commerce backend. C. Migrating a relational MySQL schema to Amazon DynamoDB, a NoSQL key-value store, requires extensive application refactoring and data modeling changes. Here's a useful exam tip. When asked to improve availability for a legacy monolithic EC2 app with minimal code changes, decouple the tiers. Put the web/app tier in an auto-scaling group behind an ALB, and move the database to Amazon RDS or Aurora multi-availability zone. Question number 381. Let's go. A development team uses AWS Code Pipeline and AWS Code Build to deliver a Python-based web service. As part of a new quality assurance mandate, the pipeline must execute unit tests and generate a code coverage report. If the calculated code coverage falls below 80%, the pipeline execution must immediately fail before the code proceeds to the deployment stage. Which solution implements this quality gate natively? Choices. Option A. Create an AWS Lambda function that downloads the source code, runs unit tests, and calculates coverage. Add a Lambda invoke action to the pipeline. Schedule an Amazon Event Bridge rule to pull the Lambda logs and halt the pipeline if coverage is under 80%. Option B. Define a code build project where the build spec.yml executes the unit tests and generates a code coverage report. Add a code build test action to the pipeline. Configure the code build project's test reporting feature or build script to exit with an error code if the coverage metric is below 80%. Option C. Deploy a Jenkins server on an Amazon EC2 instance. Configure Jenkins to run the unit tests and output the coverage report. Add a Jenkins test action to the pipeline and insert a manual approval action to review the coverage report before continuing. Option D. Create an AWS step function state machine that runs the tests. Add a step functions invoke action to the pipeline. Configure the state machine to return a failure state to the pipeline if coverage falls below 80%. In this case, choose option B. Define a code build project where the build spec.yml executes the unit tests and generates a code coverage report. Add a code build test action to the pipeline. Configure the code build project's test reporting feature or build script to exit with an error code if the coverage metric is below 80%. AWS Code Build natively supports running test frameworks like PyTest or coverage.py via commands specified in the build spec.yml file. Code Build can also parse test coverage reports. By evaluating the coverage percentage within the build script, Code Build can deliberately return a non-zero exit code if the threshold is not met. A non-zero exit code causes the code build run to fail, which subsequently causes the code pipeline stage to fail automatically, stopping the deployment. The remaining options can be eliminated because A. Event bridge polling Lambda logs is asynchronous and disjointed. It cannot reliably halt an actively running pipeline stage synchronously. C. Deploying and managing a Jenkins server introduces unnecessary infrastructure overhead. Furthermore, requiring a manual approval action violates the requirement for the pipeline to automatically generate and fail. D. While step functions can orchestrate complex workflows, using it just to run tests when code build is explicitly designed for building and testing code is an anti-pattern that increases complexity. Keep this point in mind for the exam. To fail a code pipeline stage based on test results, static analysis, or code coverage, run the tool in AWS Code Build and ensure the script exits with a non-zero status code if the criteria are not met. Code Build will handle failing the pipeline stage. Question number 382. The focus now shifts to CloudWatch metrics. An e-commerce application logs transactional data in JSON format directly to an Amazon CloudWatch logs log group. Each log event includes a metadata field representing the transaction outcome, formatted as either status, success, or status, failure. Management wants a visual dashboard that continually tracks and displays the total number of successful transactions over time. A DevOps engineer needs to build this with the least operational overhead. Which solution satisfies this requirement? Choice A. Provision an Amazon OpenSearch Service domain. Apply an OpenSearch Service subscription filter to the log group. Create an OpenSearch dashboard's visualization querying for status, success. Choice B. Configure a CloudWatch logs metric filter on the log group with a filter pattern matching $.status equals success. Use the generated metric to create a graph on a CloudWatch dashboard. Choice C. Create an Amazon Kinesis data stream and subscribe it to the log group. Deploy an AWS Lambda function to consume the stream, filter for success statuses, and publish a custom metric. Graph the metric on a CloudWatch dashboard. Choice D. Set up a CloudWatch logs subscription filter that triggers an AWS Lambda function. Program the function to parse the JSON logs and issue a put metric data API call for every successful transaction. Graph the metric on a CloudWatch dashboard. The right response is option B. Configure a CloudWatch logs metric filter on the log group with a filter pattern matching $status equals success. Use the generated metric to create a graph on a CloudWatch dashboard. This works because CloudWatch logs metric filters natively scan incoming log events for specific patterns and extract values to automatically publish CloudWatch metrics. Because the logs are in JSON format, a JSON filter pattern, for example, $status equals success, perfectly isolates the target data. This solution requires zero compute resources, like Lambda or OpenSearch, and is entirely managed within CloudWatch, providing the lowest operational overhead. The resulting metric can be easily added to a CloudWatch dashboard. A. Deploying and maintaining an Amazon OpenSearch service cluster introduces significant infrastructure costs and operational overhead just to visualize a single metric. C. Provisioning Kinesis and Lambda to process logs is a heavy, custom architecture that requires code maintenance and incurs unnecessary costs. D. Using a Lambda subscription filter to call put metric data duplicates a feature that CloudWatch metric filters handle natively, increasing cost and operational burden. The main takeaway is whenever you need to generate numerical data or alarms based on textual patterns in CloudWatch logs, especially JSON, use CloudWatch logs metric filters. They are native, serverless, and require no custom code. Question number 383. Scenario. A gaming company operates a real-time multiplayer leaderboard application hosted on Amazon EC2 instances. To accommodate a growing global player base, the company has deployed the application fleet into multiple AWS regions. The application relies entirely on WebSocket connections to stream dynamic score updates instantly to players. A DevOps engineer must configure the global routing architecture so that players connect to the deployment in the region that provides the lowest possible network latency. Which network architecture provides the lowest latency for this WebSocket workload? Option A. Provision a network load balancer, NLB, in each region. Deploy an AWS Global Accelerator Standard Accelerator and configure endpoint groups containing each region's NLB. Point the application's Amazon Route 53 alias record to the accelerator's DNS name. Option B. Provision an application load balancer, ALB, in each region. Configure an Amazon CloudFront distribution using an origin group containing all regional ALBs. Point the application's Amazon Route 53 alias record to the CloudFront distribution domain. Option C. Provision an application load balancer, ALB, in each region. Create an Amazon Route 53 A record utilizing a latency-based routing policy, and add the IP addresses of all ALBs as the record values. Option D. Provision a network load balancer, NLB, in each region. Create an Amazon Route 53 A record utilizing a multi-value answer routing policy, adding the IP addresses of all regional NLBs. The best choice is option A. Provision a network load balancer, NLB, in each region. Deploy an AWS Global Accelerator Standard Accelerator and configure endpoint groups containing each region's NLB. Point the application's Amazon Route 53 alias record to the accelerator's DNS name. Let's look at the reasoning. WebSockets require persistent, long-lived TCP connections. AWS Global Accelerator provides static anycast IP addresses and routes user traffic through the heavily optimized AWS global network directly to the optimal regional endpoint based on health and lowest latency. Combining Global Accelerator with network load balancers, which excel at long-lived, high-throughput TCP connections, provides the lowest possible latency and most consistent network performance for global real-time applications. Let's quickly check the incorrect choices. B. CloudFront supports WebSockets, but CloudFront origin groups are designed for active/passive high-availability failover, not for routing users to their lowest latency regional origin actively. C. While Route 53 latency-based routing directs traffic to the lowest latency region, it relies on standard internet routing, BGP, which is often slower and less stable than the dedicated AWS global backbone utilized by Global Accelerator. D. Route 53 multi-value answer routing provides simple DNS-based load balancing and health checking. It does not measure client latency, so it cannot ensure players connect to their closest region. Exam tip. For global workloads requiring the absolute lowest latency for non-HTTP traffic or persistent TCP/UDP connections like WebSockets, AWS Global Accelerator is superior to DNS-based routing because it avoids public internet congestion by ingressing traffic at edge locations. Question number 384. Let's go. We're moving on to high availability. A financial services firm is re-architecting its trading dashboard for AWS. The dashboard relies heavily on persistent WebSocket connections to stream market data. Because the application maintains complex state locally on the backend servers during a session, the architecture strictly requires sticky sessions, session affinity. The application must be highly available across multiple AWS regions and must be accessible to users globally with minimal latency. Which architecture will meet these constraints with the least operational overhead? Choices. Option A. Provision an application load balancer, ALB, in each operating region. Enable cross-zone load balancing and configure sticky sessions on the ALBs. Manage global traffic by integrating the ALBs with Amazon Route 53 utilizing a latency-based routing policy. Option B. Provision a network load balancer, NLB, in each operating region. Enable cross-zone load balancing and configure sticky sessions on the NLBs. Manage global traffic by integrating the NLBs with Amazon Route 53 utilizing a geolocation routing policy. Option C. Provision an application load balancer, ALB, to handle standard HTTP requests. Provision a network load balancer, NLB, in each operating region dedicated exclusively to WebSocket traffic. Enable sticky sessions on the ALB and configure it to forward WebSocket requests to the regional NLBs. Option D. Provision a network load balancer, NLB, with cross-zone load balancing active. Register IP-based targets across multiple availability zones. Distribute traffic globally using Amazon CloudFront, and implement sticky sessions by relying on source IP address preservation at the NLB tier. The answer here is option A. Provision an application load balancer, ALB, in each operating region. Enable cross-zone load balancing and configure sticky sessions on the ALBs. Manage global traffic by integrating the ALBs with Amazon Route 53 utilizing a latency-based routing policy. This is the best choice because the application load balancer, ALB, provides native support for both WebSockets and cookie-based sticky sessions, which is crucial for applications maintaining local state. By deploying an ALB in multiple regions and enabling cross-zone load balancing, the architecture achieves high availability. Amazon Route 53 with latency-based routing effectively routes global users to the region, providing the lowest network latency, satisfying all constraints with minimal overhead. Now let's rule out the other options. B. While network load balancers now support stickiness via target groups, geolocation routing maps users based on their physical location, which does not inherently guarantee the lowest network latency, which latency-based routing does. C. Using an ALB to forward traffic to an NLB adds an unnecessary architectural tier. ALB natively supports WebSockets. There is no need to split HTTP and WebSocket traffic between two different load balancer types. D. CloudFront terminating connections obscures the true client IP from the NLB, unless specific headers are passed and processed, breaking IP-based sticky sessions. Additionally, NLBs are generally L4 and lack the robust application layer stickiness of ALB. When an application requires robust session stickiness, affinity, along with WebSocket support, the application load balancer, ALB, is the native choice. Route 53 latency routing handles multi-region distribution. Next up is question number 385. Here's what is happening. A manufacturing company automatically generates specification documents and ultimately stores approved documents in a production Amazon S3 bucket that is readable by all internal staff. Documents for unannounced products are confidential and must never enter the production bucket. An unannounced product is identified by a proprietary 12-character product ID consisting of the letter P followed by 11 uppercase alphanumeric characters. This company-specific identifier is not covered by an Amazon may-see managed data identifier. Which solution ensures that documents containing the confidential product IDs are filtered before production exposure? The choices are: option A, write all documents to a staging S3 bucket. Create an Amazon may-see custom data identifier with a regular expression for the proprietary product ID pattern. Run a sensitive data discovery job on staging, and copy only objects with no matching findings to the production bucket. Option B, create the same may-see custom data identifier but run the discovery job only after documents have already been written to the production bucket, deleting matching objects afterward. Option C, run a may-see discovery job directly on the production bucket using only managed data identifiers and delete objects that produce findings. Option D, write documents to staging, run a may-see discovery job using only managed data identifiers, and copy objects with no findings to production. The right response is option A, write all documents to a staging S3 bucket. Create an Amazon may-see custom data identifier with a regular expression for the proprietary product ID pattern, run a sensitive data discovery job on staging, and copy only objects with no matching findings to the production bucket. Here's why. Amazon may-see custom data identifiers support regular expressions for proprietary data patterns, so a custom identifier can detect the company's specific product ID. Scanning in an isolated staging bucket ensures that a document is evaluated before it becomes broadly readable. Only objects without matching findings are promoted to the production bucket. Here's why the alternatives are not suitable. B. The confidential document is already exposed in the production bucket before the discovery job detects and deletes it. C. Managed data identifiers detect predefined categories of sensitive data and do not automatically cover this proprietary product ID. The skin also occurs after production exposure. D. Staging is appropriate, but managed identifiers do not detect the stated proprietary pattern, so confidential documents could be promoted. A helpful shortcut is this. Use a may-see custom data identifier when the sensitive value follows an organization-specific regex pattern. If the requirement says data must never be exposed in production, scan, and gated in staging before promotion. Next, question number 386. A hospital runs a supported Amazon RDS for Microsoft SQL Server Enterprise Edition DB instance with at least 4 vCPUs. The application uses a Route 53 name record that points to the database endpoint. The database must tolerate an availability zone failure and also have a continuously replicated copy in another AWS region for disaster recovery. During a regional outage, recovery should be automated and should avoid waiting for a backup restore. The team wants to minimize data loss and recovery time, while recognizing that asynchronous cross-region replication does not provide a fixed replication lag guarantee. Which solution best satisfies these resilience requirements? Options. Option A. Use an Amazon RDS for SQL Server multi-availability zone deployment in the primary region and create a cross-region read replica. During a regional disaster, automate promotion of the cross-region replica to a standalone DB instance and update the Route 53 name record to the promoted endpoint. Option B. Use an RDS for SQL Server single availability zone deployment and AWS Database Migration Service, AWS DMS, to replicate to another region. Notify administrators to perform the DNS change manually during a disaster. Option C. Use an RDS for SQL Server single availability zone deployment and configure AWS Backup to create and copy backups to another region every 30 seconds. Restore the latest backup during a disaster. Option D. Use an RDS for SQL Server multi-availability zone DB cluster deployment and copy snapshots to another region every 5 minutes, restoring a cluster during a disaster. Go with Option A. Use an Amazon RDS for SQL Server multi-availability zone deployment in the primary region and create a cross-region read replica. During a regional disaster, automate promotion of the cross-region replica to a standalone DB instance and update the Route 53 name record to the promoted endpoint. The main reason is RDS for SQL Server multi-availability zone provides in-region high availability. For supported SQL Server Enterprise Edition instances, RDS read replicas can be created in another region. Read replica replication is asynchronous, and a cross-region replica can be promoted to a standalone writable DB instance during disaster recovery. Automating promotion and the Route 53 update avoids a backup restore recovery path and minimizes recovery time. The other choices do not work because B. Single availability zone does not satisfy the availability zone resilience requirement, and a manual DNS change is inconsistent with automated recovery. C. Single availability zone does not provide in-region high availability, and AWS Backup cannot create cross-region database backups every 30 seconds. Restore-based recovery is also slower than promoting a continuously replicated replica. D. RDS multi-availability zone DB clusters are not the SQL Server multi-availability zone architecture described by RDS, and periodic snapshot restore is not a continuously replicated regional standby. Here's a useful exam tip. For RDS for SQL Server, distinguish multi-availability zone high availability from read replica disaster recovery. SQL Server read replicas are supported only for Enterprise Edition on supported instance sizes, and replication is asynchronous, so do not promise a fixed subminute or PO. Next up is question number 387. We're moving on to operational automation. Here's what is happening. A security compliance team mandates that every Amazon EC2 instance launched across the enterprise must use an approved, hardened Amazon Machine Image, AMI. The enterprise manages dozens of AWS accounts via AWS organizations. The standard AMI must be rebuilt monthly to include the latest OS security patches and must be immediately accessible to all member accounts in the organization. A DevOps engineer needs to automate this build and distribution process. Which solution accomplishes this with the most operational efficiency? The choices are: Option A. Define a pipeline using EC2 Image Builder. Configure the pipeline's distribution settings to share the generated AMI with the AWS organization. Set the pipeline schedule to execute monthly. Option B. Create an AWS Systems Manager automation runbook that provisions an EC2 instance, applies patches, and captures an AMI. Deploy the runbook to all member accounts and trigger it monthly via EventBridge. Option C. Construct an AWS code pipeline workflow triggering AWS code build to execute Packer scripts to build the AMI. Implement a custom AWS Lambda function to update AMI permissions for all organization accounts. Schedule the pipeline monthly. Option D. Develop an AWS CloudFormation template that provisions the patched AMI. Create an AWS Lambda function triggered monthly to deploy this template into every member account utilizing AWS CloudFormation stack sets. In this case, choose option A. Define a pipeline using EC2 Image Builder. Configure the pipeline's distribution settings to share the generated AMI with the AWS organization. Set the pipeline schedule to execute monthly. EC2 Image Builder is a fully managed AWS service specifically designed to automate the creation, management, and distribution of secure server images. It natively supports scheduled pipeline executions, for example, monthly, and its distribution settings can natively share the resulting AMI across an entire AWS organization or specific organizational units, OUs, without requiring custom scripting or complex IAM management. This represents the absolute lowest operational overhead. The remaining options can be eliminated because B. Deploying runbooks to execute locally in every member account generates duplicate AMIs in every account rather than a single standardized AMI shared globally, wasting compute resources and complicating tracking. C. While Packer and Code Build is a valid way to build AMIs, writing custom Lambda functions to parse organizations' APIs and manage cross-account AMI permissions introduces heavy, unnecessary operational overhead compared to Image Builder. D. CloudFormation stack sets deploy infrastructure resources. They do not inherently compile, patch, and build AMIs from scratch. Keep this point in mind for the exam. Whenever a scenario requires automating the build, patching, testing, and multi-account distribution of AMIs, EC2 Image Builder is the native, most operationally efficient choice. Question number 388. Scenario. A media company runs a serverless voting application during live television broadcasts. The backend consists of an Amazon API Gateway REST API, AWS Lambda functions, and an Amazon DynamoDB table. Currently, the entire stack resides in a single AWS region. In preparation for a global broadcast event, the architecture must be expanded to be highly available across 2 AWS regions. To provide the best user experience, incoming viewer traffic must automatically be directed to the region offering the lowest network latency. Which combination of steps is required to achieve this architecture? Choose 3. Identify all valid responses. Option A. Replicate the REST API configuration and deploy the AWS Lambda functions in the second AWS region. Option B. Configure an Amazon Route 53 a record utilizing a multi-value answer routing policy targeting both APIs. Option C. Convert the existing Amazon DynamoDB table into a global table spanning both regions. Option D. Define an Amazon Route 53 alias record utilizing a latency-based routing policy targeting both APIs and attach health checks. E. Establish an Amazon Route 53 alias record utilizing a failover routing policy, designating the primary region as active and the second as passive. F. Define a global secondary index, GSI, on the DynamoDB table and project it to the second region. You should choose option A. Replicate the REST API configuration and deploy the AWS Lambda functions in the second AWS region. Option C. Convert the existing Amazon DynamoDB table into a global table spanning both regions. And option D. Define an Amazon Route 53 alias record utilizing a latency-based routing policy targeting both APIs and attach health checks. This works because to deploy a highly available, multi-region serverless backend, the compute layer, API Gateway, and Lambda must be explicitly deployed in the new region. The data layer, DynamoDB, must be synchronized across both regions, which is natively achieved by converting the existing table to an Amazon DynamoDB global table. Finally, to ensure users connect to the region providing the best performance, Amazon Route 53 must be configured with a latency routing policy pointing to the regional API endpoints, protected by health checks to fail over if a region experiences an outage. B. Multi-value answer routing distributes traffic randomly, like round robin. For simple load balancing, it does not measure or route based on geographic network latency. E. Failover routing operates strictly in an active/passive mode. The scenario dictates routing based on least latency, which implies an active/active multi-region deployment. F. A global secondary index, GSI, provides alternative query patterns within a single DynamoDB table. It does not replicate data across AWS regions. The main takeaway is for an active/active serverless multi-region architecture with lowest latency requirements. Use API Gateway/Lambda deployed in multiple regions, DynamoDB global tables for data synchronization, and Route 53 latency routing. Question number 389. Scenario. A financial institution manages a large multi-account AWS environment with AWS organizations and AWS Control Tower. The central security team defines baseline security controls and compliance resources in an AWS Cloud Development Kit, AWS CDK, application stored in source control. The controls must be deployed consistently to specified organizational units and AWS regions. Any future commit that changes the CDK application must automatically update the targeted stack instances without a custom deployment orchestrator. Which approach meets these requirements with the least operational overhead? Choices. Option A. Compile the security control construct into a CloudFormation macro. Create a stack set that references the macro and rely on the macro itself to detect future source code commits. Option B. Model an AWS CloudFormation stack set in the AWS CDK by using CFN stack set with service managed permissions and the required OU/account and region deployment targets. Store the CDK application in source control and use code pipeline with code build to run CDK synth and CDK deploy automatically when the source changes. Option C. Add the CDK construct directly to an AWS Control Tower account factory configuration and rely only on new account enrollment to update every existing account and region after each code change. Option D. Synthesize the CDK application to a static CloudFormation template and maintain a custom Lambda function that watches for template changes and manually calls stack set update operations. The best choice is option B. Model an AWS CloudFormation stack set in the AWS CDK by using CFN stack set with service managed permissions and the required OU/account and region deployment targets. Store the CDK application in source control and use code pipeline with code build to run CDK synth and CDK deploy automatically when the source changes. Let's look at the reasoning. AWS CDK exposes the CloudFormation AWS CloudFormation stack set resource through the CFN stack set construct. A service-managed stack set can target AWS organizations, OUs/accounts, and multiple regions. A source-triggered code pipeline/code build deployment supplies the missing automation boundary. Each committed CDK change is synthesized and deployed, and CloudFormation stack sets propagates the updated template to the targeted stack instances. Let's quickly check the incorrect choices. A. CloudFormation macros transform templates during CloudFormation processing. They do not monitor source control or orchestrate multi-account deployment updates. C. Account factory enrollment focuses on account provisioning and does not by itself make every existing account and region update whenever this CDK source changes. D. A custom Lambda function that watches templates and calls stackset AP adds code and operational overhead that code pipeline plus CDK deployment avoids. Exam tip. CDK can define a CloudFormation stack set with CFN stack set, but source commits are not self-deploying. Use a CI/CD trigger to run CDK synth/deploy, then let stack sets propagate the change across accounts and regions. Question number 390. This question takes us into artifact management. Consider this situation. A software company uses a development account for engineers and a production account for production workloads. Developers publish shared Python libraries, but they must have direct publishing permissions only to the development repository. A package can reach the production repository only after an automated integration test pipeline succeeds. The company wants a native code artifact promotion workflow that can operate across the two accounts. Which architecture best satisfies the security and promotion requirements? Here are the options. Choice A. Create separate code artifact domains in the development account and production account. After a code build test succeeds, call copy package versions to copy the package directly from the development domain to the production domain. Choice B. Use one code artifact domain that contains a development repository administered by the development account and a production repository administered by the production account. Use domain and repository resource policies so developers can publish only to the development repository. Trigger code pipeline from code artifact package events, run integration tests, and on success use copy package versions to promote the validated package to the production repository. Choice C. Use versioned S3 buckets in both accounts as the package repositories. Copy the package to production first, run integration tests there, and delete it if the tests fail. Choice D. Create only a production code artifact repository and allow developers to publish packages directly to it. Run tests after each production publication. The answer here is option B. Use one code artifact domain that contains a development repository administered by the development account and a production repository administered by the production account. Use domain and repository resource policies so developers can publish only to the development repository. Trigger code pipeline from code artifact package events, run integration tests, and on success use copy package versions to promote the validated package to the production repository. This is the best choice because a code artifact domain can contain repositories administered by different AWS accounts, with cross-account access controlled by domain and repository resource policies. Code artifact emits event bridge events when package versions are published, which can start code pipeline. After integration tests pass, copy package versions can promote the package between the development and production repositories because both repositories are in the same code artifact domain. Now let's rule out the other options. A. Copy package versions only copies package versions between repositories in the same code artifact domain, so it cannot directly copy from one domain to another. C. S3 does not provide the native Python package repository and promotion semantics of code artifact, and the package is exposed to production before tests succeed. D. Allowing developers to publish directly to production violates environment isolation and performs validation only after the package is already available in production. For code artifact package promotion, keep the source and destination repositories in the same domain. Repositories in that domain can be administered by different accounts. Event Bridge can start code pipeline on a package version event. Question number 391. Let's go. A DevOps engineer is configuring a continuous delivery process for a web application. The application consists of a React frontend hosted in an Amazon S3 bucket and a Node.js backend running on Amazon EC2 instances. The source code for both components is stored in a single AWS code commit repository. The business requires that front-end and back-end updates can be built, tested, and deployed independently of one another whenever developers push changes to the main branch. Which solution will meet these deployment requirements with the least operational overhead? Option A. Create a single AWS code pipeline that sources from the code commit repository. Configure parallel AWS code build actions for the front-end and back-end. Use a single AWS code deploy stage to handle both the S3 upload and the EC2 deployment simultaneously. Option B. Create two separate AWS code pipelines, one for the front-end and one for the back-end. Configure the source stage of each pipeline to trigger on changes to the code commit repository. Use AWS code build in each pipeline, and use Amazon S3 as the deployment provider for the front-end and AWS code deploy for the back-end. Option C. Create a single AWS code pipeline. Configure two sequential build stages using AWS code build. Use AWS code deploy for the backend EC2 deployment stage, and use an AWS Lambda function action to copy the front-end build artifacts to the S3 bucket. Option D. Create an AWS code build project that builds both the front-end and back-end artifacts. Trigger the build using an Amazon Event Bridge rule on code commit push events. Use an AWS step function state machine to coordinate the S3 upload and the AWS code deploy EC2 deployment. The best choice is option B. Create two separate AWS code pipelines, one for the front-end and one for the back-end. Configure the source stage of each pipeline to trigger on changes to the code commit repository. Use AWS code build in each pipeline, and use Amazon S3 as the deployment provider for the front-end and AWS code deploy for the back-end. Here's why. Creating two distinct pipelines is the most operationally efficient way to satisfy the requirement for independent builds and deployments. By decoupling the pipelines, a front-end change can progress to production without waiting for or risking a backend deployment, and vice versa. Both pipelines can trigger off the same source repository using path-based filtering in V2, or by pulling the source and selectively building. Here's why the alternatives are not suitable. A single pipeline deploying both simultaneously couples the deployments together, violating the requirement to deploy independently. C. A single pipeline orchestrating sequential deployments still fundamentally ties the release lifecycles together, preventing independent deployment. D. Using event bridge and step functions introduces unnecessary custom orchestration overhead when code pipeline natively supports this CI/CD workflow. A helpful shortcut is this. When requirements dictate that components of a monolithic source repository must be deployed independently, split the release process into multiple decoupled pipelines rather than trying to conditionally skip stages within a single pipeline. Next, question number 392. Next, let's move into multi-region resilience. A company operates an image processing platform in the US, East, 1 region. Users upload images via a network load balancer, NLB, to Amazon Elastic Container Service, Amazon ECS, Fargate tasks. The container images are stored in Amazon Elastic Container Registry, Amazon ECR. The raw images are stored in an Amazon S3 bucket, and processing metadata is saved in an Amazon DynamoDB table. Amazon Route 53 handles the application's DNS. The company must expand this workload to the EU, West, 1 region in an active-active, highly available configuration. A DevOps engineer must implement this expansion while minimizing changes to the application code and deployment configurations. Which combination of steps will meet these requirements? Choose 3. More than one answer may be correct. Options. Option A. Enable cross-region replication on the existing ECR repository to EU, West, 1. Deploy an NLB and ECS Fargate cluster in EU, West, 1. Update the Route 53 record to use a latency-based routing policy, targeting both NLBs. Option B. Deploy the container images to an Amazon EC2 auto-scaling group in EU, West, 1. Configure an application load balancer to route cross-region traffic to the existing ECS tasks in US, East, 1 if the EC2 instances fail. Option C. Convert the DynamoDB table to a global table with a replica in EU, West, 1. Update the application configuration so that the Fargate tasks in each region read and write to their local regional DynamoDB endpoint. Option D. Update the Fargate tasks in both regions to read and write exclusively to the original DynamoDB table in US, East, 1 to ensure strong read consistency globally. E. Create an S3 multi-region access point. Configure a new S3 bucket in EU, West, 1, and enable bidirectional S3 cross-region replication between the 2 buckets. Update the application to use the multi-region access point ARN for S3 operations. F. Modify the existing continuous delivery pipeline to build 2 separate versions of the container image, one configured for US, East, 1 and one for EU, West, 1, and deploy them to separate regional registries. The correct answers are Option A. Enable cross-region replication on the existing ECR repository to EU, West, 1. Deploy an NLB and ECS Fargate cluster in EU, West, 1. Update the Route 53 record to use a latency-based routing policy targeting both NLBs. Option C. Convert the DynamoDB table to a global table with a replica in EU, West, 1. Update the application configuration so that the Fargate tasks in each region read and write to their local regional DynamoDB endpoint. And Option E. Create an S3 multi-region access point. Configure a new S3 bucket in EU, West, 1, and enable bidirectional S3 cross-region replication between the 2 buckets. Update the application to use the multi-region access point ARN for S3 operations. The main reason is these 3 steps establish a fully active multi-region architecture with minimal application refactoring. ECR replication automates image delivery. Route 53 latency routing directs users to the closest healthy ECS cluster. DynamoDB global tables handle multi-region data replication while allowing local reads/writes, reducing latency. S3 multi-region access points provide a single global ARN, allowing the application code to remain identical across regions, while AWS handles routing to the closest bucket. The other choices do not work because B. Deploying to EC2 instead of Fargate changes the compute architecture unnecessarily and introduces AMI management overhead. D. Forcing the EU, West, one cluster to read/write across the world to us, East, one introduces massive latency and creates a single point of failure. F. Modifying the CI/CD pipeline to build two different regional images adds significant operational overhead when ECR natively handles cross-region image replication. Here's a useful exam tip. For multi-region storage, S3 multi-region access points and DynamoDB global tables are the preferred AWS native mechanisms to achieve active resilience with minimal application code changes. You have completed set 21 of the DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.